All right, so this video is going to be on 8.2. So let's go ahead and do that. And let's move this up here. Okay, so we're talking about rolling motion or moment of inertia. This is 8.2, so remember we did 8.1, then we skipped over and did 8.3, and now we're coming back and doing moment of inertia. And there's actually a problem in 8.3 that kind of gets explained after going over 8.2, but because of our lab situation, we thought it'd be better to do 8.3 first. All right, so let's talk about what rolling motion is. So think about a bicycle tire or any tires. So when they're rolling, there's no slipping between the tire and the ground. They're just kind of rolling along. The wheel rotates about its axis, and at the same time that it's rotating, it's also moving in a straight line. So with rolling motion, you have a combination of rotational motion and linear motion both. So you have both linear velocity and angular velocity going on at the same time. And so because of this, the forward motion of the axle cancels out any backward motion that happens at the bottom of the wheel. So at the top of the wheel, let's see. So here's the top of the wheel. So at the top, you're moving forward, and at the bottom, there might be a backwards motion. And those two things cancel out. So that's why the instantaneous speed at the bottom of the wheel, so how fast it's moving at the bottom of the wheel, is always 0. At the top part of the wheel, it's important to remember that your speed is 2 times the average velocity or what the car's speed is. So if your car is going 45 miles per hour, then, and that's what reads on the speedometer, then the speed at the top of the wheel, so if there was something embedded in that top of the wheel, how fast the top of that wheel goes would be 2 times the 45 miles per hour. So it would be going 90 miles an hour. Okay. And that's the thing that you need to take into account for one of our exercises in 8.3. The other thing you need to take into account is when it talks about different shapes. So, and we'll learn this in just a second, but different shapes have different moments of inertia. So they have different formulas that go with them. Okay. So, and we're going to be doing a whole lab on that where we're comparing how a sphere or a hoop or a disc, how all those things roll down an inclined plane and how those velocities change depending on the shape. All right, so due to its inertia, remember inertia is just that everything's going to keep going in a straight line until, or the way it's been going, until another force acts on it. So due to its inertia, object at rest or an object moving keeps going and resists changes to that motion. Same thing for rotational motion. So an object is going to keep on rotating, and it's going to resist changing that until another force acts on it. So every object has what we call a moment of inertia, and we label that as I, which determines how easy or how hard it is to change its rotation. Objects with large moments of inertia are very hard to stop rotating. So an example, if you think about playing on a merry-go-round, to get that merry-go-round going, it's kind of difficult. You have to put in a lot of force at first to get it moving because it's so big. But if you compare that to a baseball, the force that's required to cause that baseball to rotate is relatively small compared to that of the merry-go-round because, again, the size is smaller. So that's what we're talking about with moment of inertia. Oops. Come on, move on. There we go. So here's an example. Experiments show that objects' moments of inertia depend linearly on the mass of the object and the square of the distance to the object's axis of rotation. So for the most part, an object's moment of inertia can be determined with that particular equation. It's mass times r squared, or its distance from the radius squared. Radius meaning the axis of rotation. Now, the shape of that object is going to affect that as well. So we actually have more than one equation for moment of inertia, okay? The moment of inertia for an entire system, of course, would depend on the moments of inertia for each object in that system. So we simply add them all up together, okay? So in a system, the moment of inertia is the sum of all the moments of inertia of each particular object in that system. So here's all of the formulas that I was referring to. So you have all of these shapes, and each shape has its own formula for moment of inertia. You do not have to memorize all of these. You will be given these on a test if you need to know them. But you just need to recognize if something says a disc rotating versus a hoop rotating, that's going to be a different moment of inertia. So you can see a hoop is I equals mr squared, whereas if you have a disc, that is I equals 1/2 mr squared. So you've got to make sure you're paying attention as you're reading the question and know which thing you are looking at, okay? For linear motion, the kinetic energy, so we talked about kinetic energy and linear motion, and you remember it was 1/2 mv squared. Okay, so when we talk about things that are rotating, we just replace linear speed with angular speed, and we replace mass with moment of inertia. Okay, so same setup, but we replace m with I and v with omega for angular speed and moment of inertia. So here is the actual formula for rotational kinetic energy right here. So we have 1/2 I omega squared. Units are still the same, just like we've seen throughout this chapter. The units stay pretty much the same. Okay. So this table is in your book, and I would make sure that I looked at it. I wouldn't memorize it or anything, but just looked at it so that you kind of make sure you understand what's what. And these just give the linear quantities versus the angular quantities. Okay. So linearly, when we talk about force, when we're talking about it in rotationally, we're talking about torque. And momentum is a P for linear qualities. Angular momentum is a I. Linear velocity, angular velocity is an omega. Okay. Or I'm sorry, that's not an I, that's an L. My eyes are going bad. So angular momentum, L, is just equal to, just like regular momentum is mass times velocity, angular momentum is moment of inertia times angular speed. Okay, other than that, all the same rules, all the same laws, all the same things apply. Okay. And that leads us to torque. Okay, so that's it for 8.2. All right, hope you have a great day.